This is joint work with Pascal Bercher and David Ahale, my boss. And so a little motivation for this, this is actually the first half of my talk. The second half will be yesterday. I hope you'll be there. So we were using at the NRL, we're using a Bluefin 21. This is a AUV with a highly configurable payload. You can rip out all the sensors and fill it with batteries, or you can rip out the batteries and put in sonar and have a little bit shorter mission. It's used for the Malaysian Airliners Flight 370 search, but NRL recently put it through the ringer distance-wise with a 500-kilometer, 109-hour endurance mission. And so this is part of at NRL of a long-duration autonomy program. And as part of this, we are incorporating a hierarchical task network planner. So this encodes HTNs in general encode procedural knowledge, generally strategies about how to solve a problem quickly. And in this case, it's important because the AUV, anytime we spend planning, is burning CPU hours, and which could have been used to extend the mission instead, with a limited battery life. And this is where it gets story time, because if you were here last time at ICAPS, I was really excited about HTN heuristics, and so I came back to NRL and I said, Mark, who's leading up the actual programming effort, you have your HTN planner. I really want to incorporate HTN heuristics, domain-independent heuristics into your planner. And he said, great. And so I went off and I started. I think I got at least 3 or 4 lines into my program when I realized I had a critical problem. If I got done, I wouldn't have anything to compare it against. So we want a domain-independent heuristic planner, or domain-independent HTN heuristics. It's not fair to compare it against classical planning with domain-independent heuristics, because that doesn't have the procedural knowledge incorporated. It's not really fair to compare it against HTN planners without heuristics, because those are using hand-encoded search knowledge, such as method ordering or some prologue-like search controls. So I thought, I have a solution. I'm going to translate the HTN knowledge into classical planning. Then it's operating on the same domain knowledge. That's great. I went off and I wrote the translator. It's automatic for a certain class of HTNs. And then as I was writing up the paper, I have another problem. I don't know what HTN problems I can translate. And so that's where we got to this paper, which is complexity of HTN planning and of various classes of HTN planning. And now I can go back and finish the translation paper so I can start the heuristics paper. And if you're wondering if we're going to get back to this AUV at the end of the slides, don't worry, we will, maybe next year. So HTN planning, we've been talking about it for a little bit, and I haven't actually told you what it is. So HTN planning, the purpose of it is to complete a task. So this is different from classical planning, where it's to get to a goal. Tasks are activities which are either primitive, which we know how to perform directly. They can correspond to, say, a motion controller we have on the craft, or they're non-primitive, which mean there are abstract tasks such as traveling from home to Los Angeles, which we need to break down into executable steps. We do this in a recursive manner, breaking abstract tasks down. We can get a hierarchy. They can be recursive, which gives us some of our expressivity with them. Decomposition is done with a set of methods, which are recipes on how to accomplish a task. So to travel from home to Los Angeles, we might decompose it first into buying an airplane ticket, traveling to the airport, flying between airports, and then traveling from the last airport to Los Angeles. So we have to break those down too. So each of those further decompose. So what is a method? A method is a pair between an abstract task or non-primitive task. Oops, sorry, wrong slide. I'll get back to that later. So why do we study HTN complexity? HTNs are a model for planning with procedural knowledge. So it's a fairly simple model too. So it corresponds to other things like we can translate HTNs in the Congo log, and I'm pretty sure we can translate back and hopefully preserve classes of problems. That I haven't figured out yet. HTN planning is in general undecidable though. So, but most HTN planners are sound and complete. However, the undecidability means that there are very small problems for which a given set of planners will not return. This is kind of unfortunate for a lot of such applications of HTN planning. So we may want to be doing model checking, especially before we send out our AUV. We want to make sure that no matter what decomposition it takes, a certain property does or does not hold. We can't do that if the problems are semi-decidable. Also, it's useful for the case I mentioned, the translation-based planning, where I want to take an HTN problem, translate it into domain-independent planning, and make use of any number of the many heuristics that we've developed as a community. Fortunately, if you throw a stick at an HTN problem, it probably becomes decidable. So there are many different ways. Today we're going to study method structures and how they impact decidability and complexity. So in general, this is whether a method's tasks are totally ordered or whether they're partially ordered and can be interleaved. Where in the method recursion can occur. So you've had programs, you've seen whether they're tail recursive or whether they're not recursive at all, or they're recurse somewhere in the middle. And whether the domain is relational, whether it has variables, we're planning a non-propositional or not. But we're not going to study that one today. We're going to study the first two. Now we're back to methods. Sorry. A method is a pair between a non-primitive task and a task network. A task network is a partial order of over tasks. So here we have the method for work, and followed by two primitive tasks that decomposes into two primitive tasks, drink and write, followed by the work itself. So this is a recursive method, and the arrows represent ordering constraints. So drink and write can occur in any order, but they must occur before we do more work. So we decompose a task in the network by replacing a node with the method's corresponding network. So if we start off with an initial task network containing just work, we can decompose it with the method above to drink and write and then work, and decompose it again to drink, write, and work. We can keep on going to get whatever size task or work we want. So, what types of recursion and can we define here? So this is acyclic HTN planning. Acyclic HTNs are where a set of methods has no recursion. So over on the right, we have a totally ordered acyclic method, because it has to be acyclic because all the tasks are primitive. That's just drink followed by write. We have a partially ordered method for more. To work more, we work, and another partially ordered method for workaholic, and work more. This defines a tree, so we can actually generate as much work as we want. So if you ever thought, oh, my workload is just increasing exponentially, well, we can make it happen. There's also a class, there's actually two classes here, called regular and tail recursive. Regular is after the language. This is where the methods are only allowed to recurse through the last task. In regular methods, all the other tasks except for the last task have to be primitive. There's a generalization of this called tail recursive, where the last task can be non-primitive. However, it can't recurse back through this method. Can't recurse back through this method and still be called tail recursive. There's also a relatively understudied class of HTNs, which is arbitrary recursion. So this is the rest of HTN planning. Partially ordered arbitrary problems are what gives HTN planning its undecidability. So you can express the intersection of context-free grammars, and this, of course, is a semi-decidable problem. Over here, we see an example of, a method for a living where we work and sleep and live interchangeably there, so that accounts for 16-hour shifts. But down below, we have a method for work, which is just we brew our coffee, we do work, and then we drink. This makes sure we have paired brew and drink actions between. Totally ordered problems are kind of interesting because you don't see people write these. if you're a planning expert and you're writing something for your specifically for your AUV, you're never going to write, as far as I know, a arbitrary problem. In general, for SHOP 2 style planning, in general, state progression. I'm not going to get too far in that. I haven't personally seen one like that. However, there's kind of a natural source of totally ordered HTN problems with arbitrary recursion, and that's programs. So Everin Sirin in 2004 did a translation of web services into HTN Planning for purposes of composing web services together, and that's where you can get arbitrary recursion. And our current set of planners, and even our current set of algorithms that we can implement in these planners, aren't really set up for this type of structure. We know that they can be, and the paper goes into showing the complexity of this, but we don't actually have it yet. So that's a new application area waiting for someone to go and implement it. We'll see if someone will pay me for it or not. So you can also encode, it's relatively easy to encode two-player game tree search in totally ordered HTN planning. So that brings us to the end of our talk. The propositional HTN complexity, given these set of features, right? Partially ordered, so totally ordered on the left, partially ordered on the right. We can categorize all the classes of HTN planning by their method structure here. And this is just for propositional. It's extended to the variables in the paper. It's okay if you're not into complexity theory. Here's how you can think of these. If it's semi-decidable, there's no translation downwards. So for these arbitrary problems, we have no translation in general to tail recursive problems. Otherwise, if you're, say, X space, there's to translate down without getting rich by proving some important results in complexity theory, you're going to have to take an exponential hit in the size of the problem of the translation. So this isn't true if you translate if it doesn't add. So going down 2 doesn't necessarily mean you get doubly exponential. So here we have, this is the arbitrarily recursive HTNs that I mentioned, where we don't have a good decision procedure for them, or good algorithms for them. We don't have any translation down to tail recursive that's in polynomial time. So but on the other hand, we do have this entire class here, which we can represent as propositional strips, which is kind of great. But I still have 5 minutes left, so I'm going to abuse you with my proof techniques. Lower bound techniques. So this is kind of the meat of the paper here. So this is where we can code a bounded Turing machine into our whatever subset of HTN planning we're worried about. This is called, I kind of refer to this as the Meatgrinder technique. We take our bounded Turing machine, tape head, machine state, and a transition function over that, and we just assemble it with our propositions and actions in our state space, and then we crank it and we see if sausage comes out or not. So that it's an old technique, but it's still great. We use it in our paper for the proving that totally ordered problems are AP space, which is equivalent to X time. But if we're trying to encode a tape of exponential length in a set of propositions, which is not that big, we can't represent the whole tape at once. So instead, what we're going to do is if we look at a Turing machine and we think about its execution, right? So we have the first state that it starts in, and step 1 we have a new configuration. There's a series of tapes that represent those Turing machines, and if we concatenate them all together, this becomes a string checking problem. So it's equivalent to say that does a given Turing machine halt in k steps, or does there exist a concatenation of k Turing machine tapes that are valid given our machine definition. To check this, we just check one cell at a time. We'll check whether the first cell is equal to the kth plus 1 cell. Should be guessed by k plus 1. Check whether the second cell is equivalent to the k plus 2 cell, and so forth. So what kind of techniques do we need for this? One is is task multiplication. This looks just like I showed you before with acyclic HTNs. We can generate given a bound k. If we do k, if we double it at each size, we get to at the bottom of the tree we'll have 2 to the kth primitive actions. We also need to implement threading in our HTNs, oddly enough. So we have a synchronized method for doing stuff, which has a start primitive action where it's listening for it to be called. It does stuff. It says it's finished. And then there's an extra synchronization step because we're going to have to call a lot of these per cell of the Turing machine tape. We have methods for stepping through this, which control it. So a step, which is a call for the start, wait on the finished, a sync, which lets the sync primitive action fire and await on it. And we can coordinate a whole bunch of synchronized tasks by doing task multiplication from the previous slide. So I kind of skipped that part. So we can step 2 to the k steps by first stepping to the k. That'll get a whole bunch of synced tasks waiting on us, and then 2 to the k sync waits. So for checking cells, so this is the do stuff. We start. We have the start. We have the check 0 finished. Same for the checking and a lot of the tasks are going to have to kind of skip that. So there's a start finished for the skip. We can check whether the cell matches 2 to the k plus 1 later with a check 0, a skip to the k, and check 0. Same for check if it's 1. And then we can start mini checks. This is much like the acyclic, except for we have a skip in the middle and the 2 checks are partially ordered. So this is a divide and conquer method for it divides the string in half, does checks on both sides, and does it again below until we get to the primitive tasks. So there's a little bit of bookkeeping left. And what I like about this is that this paper, we've shown that the tail recursive totally ordered propositions or propositional HTNs are p-space complete. We have a quadratic translation to strips. There's lots of implementation issues, which I won't get into now because I'm running out of time. But there's lots of opportunities for research here. So there are very few dedicated HTN heuristics. We have some algorithmic research to do, and I'm kind of excited about that work and other people doing this too. So thank you.